In this video, we are going to look at sequences of real numbers, in particular recursive sequences, which are very similar to how we think about proof by induction. First thing we're going to do is give the definition of a sequence just generally. And then we're going to describe two different ways to define a particular sequence. One way is using closed formulas, and another way is using a recursive definition. And then we're going to show some similarities between recursively defined sequences and proof by induction. So first of all, what is a sequence? Well, let's think about in some circumstances where we use the word sequence in real life. So think of a sequence of numbers that you'd use for, say, an access code, something like that, like for your phone or for your door lock. So what are the things that matters in the numbers that you use in a code like that? Well, it matters what numbers are in the code, for sure. It matters what position the numbers are in, right? So if you have the same numbers in different positions, it won't be the same code. And then actually, if the same number appears more than once, that matters as well. That's different than the same numbers, but none of them appearing more than once. So this is kind of what a sequence of mathematics is like. The only difference with a sequence is that it is infinitely long. So a sequence is an infinite ordered list of real numbers. And the notation we sometimes use for sequences is we use A0 for the 0th term. That's like the first term, but we usually start at 0. A1 is the 1th term, the second term is A2, then A3, etc. And that's the order that the numbers are in. If we want to make it a little bit more economical, we can just write A sub n. N is the subscript. And then we can write where the n's begin, n equals 0, and then up top we write where the n's end, infinity. That just means that the sequence doesn't end. So let's look at an example. So here's the 0th element of the sequence. We got 0, we've got 1, we've got 4, we've got 9, we've got 16 and 25. And I mean, if you can see the pattern, it looks like these are just the sequence of squares. And so we have n squared from n equals 0 to infinity. So we got 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. Here's another sequence that I'm sure you've seen before. We got 1, then 2, then 6, then 24, then 120, then 720. And that is the factorial sequence. And again, the factorial sequence starts at 0. So 0 factorial is 1. And it keeps on going for all natural numbers. Now, so just to indicate that when 0 factorial is kind of the weirdo, that one's equal to 1. The other ones are defined more systematically. If you want n factorial, where n is 1 or bigger, what you do is you start at 1, you keep multiplying by the next number up until you get to n. So there are some different ways that we can define a sequence. We've seen the primary one above with the square and the factorial ones, and that is the use of a closed formula. So for n squared, we could say that a sub n is equal to n squared. N squared literally gives us a formula for a sub n. And of course, we've got to say where n starts. Usually it starts at 0, but it doesn't have to. Actually, you can start at 1 or 2 or anywhere you want, as long as you indicate that at the beginning. So this is very similar to functions. Functions can be defined using formulas as well. And then this one's a little bit different. This is you can have a recursive formula. And a recursive formula, what that does is we first tell you what the first term is, or maybe we have to tell you what the first few terms are, first 2 or 3. And then we write a recursive formula that defines each term of the sequence in terms of the ones that came before it. So if I want to find the 5th term, I can define that in terms of the 4th term, or the 3rd term, or the 2nd term, or the 1st term, etc. So we can actually do that with factorial. Let me demonstrate how we do that with 4 factorial. So how would we take 4 factorial and define that in terms of one of the factorials that go before it? Well, if I group the first 3 terms together, 1 times 2 times 3, that's actually 3 factorial. And so if I flip the order around a little bit, we get that 4 factorial is equal to 4 times 3 factorial. So what that means is, if I work my way up to 3 factorial, I get to 4 factorial by multiplying by 4. And in general, as long as n is greater than or equal to 1, we have that n factorial is equal to n times n minus 1 factorial, which again means if I know what n minus 1 factorial is, I can get to n factorial by multiplying by n. All right, so now we're going to go ahead. Now we're going to actually define the factorial sequence recursively and show you what a formal recursive definition is. So we're going to define it as follows. First of all, I'm going to tell you what the very initial term is. That's 0 factorial, which we're going to define equal to 1. And then we're going to define the rest of the terms recursively. So I'm going to define n factorial equal to n times n minus 1 factorial, where n is greater than or equal to 1. And my claim is, by defining the factorial sequence in this way, we essentially have, not just essentially, we have defined all the terms of the sequence starting with 0. Because we know the sequence at 0, that's just 0 factorial, right? 0 factorial, which equals 1. If I want to find 1 factorial, I get to use the recursive formula. If I put in n equals 1, 1 factorial is going to be 1 times 0 factorial. But the thing is, we've already defined 0 factorial to be 1, so that's 1 times 1, which equals 1. So 1 factorial equals 1. What do I do for 2 factorial? Well, if I plug in n equals 2 into the recursive sequence, I get 2 factorial equals 2 times 1 factorial, right? And then 1 factorial we found to be 1, so we get 2 times 1, which equals 2. We could do the exact same thing for 3 factorial. If we plug in n equals 3, we get 3 factorial is equal to 3 times 2 factorial. We just found 2 factorial, that equals 2, and so we get 3 times 2 is equal to 6. And finally, if we want to do 4 factorial, we get 4 times 3 factorial, letting n equal 4. And then 3 factorial we just found to be 6. What a coincidence, how convenient. 4 times 6 is 24. And we can keep on going like that. 5 factorial is going to be 5 times 4 factorial, and etc., etc. And notice that what we've done here is anytime we want to find a factorial, as long as we've proven the previous factorial, we can find it. So now we're going to define the Fibonacci sequence recursively, right? That's going to be slightly different, but the same basic concept. So for our recursive formula, here's what the recursive formula looks like. Fn is equal to Fn minus 1 plus Fn minus 2, which means that in order to find a given term, you add the two previous terms together to get it. But the thing is, when is that recursive formula going to be legitimate? For the factorial definition, we could start the recursive formula at n equals 1. Turns out the Fibonacci sequence is a little bit different. So the question is, how many initial terms do we have to define? So if I tell you that f of 0 equals 0, would we be able to find f1 using the recursive formula? Well, I'm not going to tell you exactly the answer. If you can't figure it out, maybe put it down as a question on the discussion board. But it turns out you can't define f of 1 using the recursive formula above, just knowing that f of 0 equals 0. See if you can explain why that's true. If not, go ahead and ask the question. It turns out we not only have to define f0 explicitly as f0 equals 0, we have to define f1 explicitly too. And for funsies, I'm just going to define f of 1 to equal 1. So we're going to define f of 0 equals 0, f of f1 is equal to 1. And so our complete definition is going to be f0 equals 0, f1 is equal to 1. And then for n greater than or equal to 2, we have fn is equal to fn minus 1 plus fn minus 2. So one of the things you may have recognized is a lot of the reasoning that we were using in proof by induction, we're also using to recursively define recursively define sequences. We define the first few terms explicitly. We just say what they are, right? That's kind of like the basis step, the base case for induction. And because induction, we prove that either the first case or the first few cases. Then we define an in terms of previous terms. It could be the one right before it, or it could be ones that are several terms before. And that's very similar to the inductive step, where in that case we assume the previous cases to prove the next case. And here we assume the previous terms to define the next term. And it's probably is not surprising to you that we very often use induction to prove some theorems about recursively defined sequences, and that is actually what you're going to be doing in the in-class activities. So if you look to recursively defined sequences on the PDF file included with this video, that will give you some formulas to prove using induction.